All right, so what we have here is change of variables for indefinite integrals. All right, now recall that for differentiable functions, y equals capital F of u and u equals g of x. And notice we're talking about f is a function of u, but u is a function of x. Chain rule tells us that we're going to take the derivative of f with g inside and then multiply that times the derivative of g. So, from the definition of an antiderivative, it follows that if I integrate this part here, this f prime g, g prime x, I'm going to get back to some composite function plus c. So this is summarized in the following theorem. Antidifferentiation of a composition. Let g be a function whose range is on an interval from an interval I, and let f be a function that's continuous on I. If g is differentiable on its domain and f is an antiderivative of little f on I, then if you are integrating fg times g prime of x, all you're going to get is the composition f of g, and then plus c, of course. What this is going to look like is if I let g be u, so let my inner function be u, and then g prime dx would be u prime, or would just be, this would just be du, honestly. And we'll see that in just a second. We wind up with fu plus c. Don't get cute. All right, so the change of variable technique uses Leibniz notation for the differential. That is, if u equals g of x, then if I take the derivative du, I get g prime x dx. Remember, you just take the derivative and tack that dx on it. This is really important because notice that g prime x dx, this becomes du, and f of gx becomes f of u. Now, in example 1 we're fixing to do, it shows how to apply this directly by recognizing the presence of a composition function and the derivative of that inner function g. Now note that the composite function in the integrand has an outside function f and an inside function g. We talk about this a lot when we talk about composition. Moreover, notice that there is the derivative of that inside function present as a factor in that integrand. Okay? When you see this problem, you'll understand what I'm talking about. So notice here, we have an outer function. This outer function is something squared. There's something on the inside, that's our inner function. So anytime you have some weird composition function like this, your first instinct is to do a change of variable. You're going to let whatever is inside the parentheses be u. And when you do this, you take the derivative. The derivative of u is du. The derivative of x squared is 2x. And since we're talking about differentials, we put the 2x, we put the dx on it. So notice that I have 2x dx. Well, that shows up right here. So if 2x dx is equal to du and x squared plus 1 is equal to u, then this derivative just becomes u squared du. Now remember, we're talking about a dummy index. We're talking about our index of integration. Our variable of integration is now u. So since we're integrating with respect to u, we just say u to the third divided by 3 plus c. But our problem is originally an x, so we need our answer to be an x. But u is just x squared plus 1, so this is x squared plus 1 cubed over 3 plus c. This method of change of variable is probably the most powerful tool that you're going to use when you do integration for the rest of your mathematical career. U sub is by far the most commonly used method of integration. Okay. Now notice that integrand fit the pattern: function, a composition function times the derivative of an inner function. Now we can also extend this rule considerably with the constant multiple rule. We've got this k on the front, which we can just pull out, right? Now a lot of integrands contain the essential part, the part that's got the variable, but somehow they're missing some constant multiple. Okay, like if we'd have come over here, if that 2 had not been there, that would be, it has the x, it's got the important part, what it doesn't have is that constant multiple. In these cases, all you have to do is multiply and divide by the necessary constant multiple. So let's look at this example 3. Well, example 2, we should say. So what do we have here? This is basically the same problem we had before, but instead of x, we've got, or instead of 2x, we've just got x. So once again, whatever's inside the parentheses, we're going to let be u. We take the derivative, we get 2x dx. But here's the thing, I don't have a 2x dx, I've only got an x dx. So I can multiply by 2 and also divide by 1/2 on the outside of the integral. So what this gives us is 1/2 the integral of x squared plus 1 squared times 2x dx. Now I can see this is 1/2 the integral of u squared du. So this is u cubed over 3 times 1/2 plus c. So u cubed over 6 plus c, but u cubed is just, or u is just x squared plus 1. So you wind up with x squared plus 1 cubed over 6. Now there's a different way that we can do this, and this is a way that a lot of people feel more comfortable. So let's do this. Let's erase this. And instead of solving for du, let's actually solve for dx. So let's divide by 2x. So we get that dx equals du over 2x. Now when we do this, all we have to do is a simple substitution. We've got the integral of x, this is u squared, right? And dx becomes du over 2x. So notice that the x's just cancel out, and I've got a 1/2 I can pull out front. So I'll end up with u3 over 3 times 1/2 du, u cubed over 6. I don't need a du anymore, do I? Which is x squared plus 1 cubed over 6. What we need is a plus c. Either way, you still get the same answer. Solving for dx allows you to plug it in and not have to worry about that constant multiple, but totally up to you as to how you do it. So let's do another one. Here we're going to start by rewriting this as 2x minus 1 to the 1/2 power. So we're going to let u be 2x minus 1, therefore du equals 2 dx. I don't have a 2 dx, I've got a dx, so what if I put a 1/2 out front and a 2 inside? Not 2x, just 2. So that, the 2's would cancel out and we would get back to this original, but this puts us in this form so that I can say, well, this is 1/2 u to the 1/2 du, right? 2 dx, that's du. 2x minus 1, that's u. So we add 1, we get u to the 3/2. We got the 1/2 on the outside. We divide by 3/2, which is the same thing as multiplying by 2/3. Remember, dividing by 3/2 is the same as multiplying by the reciprocal, 2/3. So we wind up with 2u, which is 2x minus 1 to the 3/2 over 3 times 2, which is 6, plus c. So, steps used for integration by substitution are summarized here. First thing, you want to choose a substitution, u equals some function. Usually it's best to choose the inner part of a composition function, such as a quantity raised to a power. Okay? We want to compute du equals the derivative of g times dx. And we're going to rewrite the integral in terms of u, and then find the integral in terms of u. Now, once we've solved that, we can go back and replace that u with our original function to get the antiderivative in terms of x. And the last thing we can always do is check our answer by differentiating. So let's come back to this problem right here. Y'all have already done this. I'm going to erase all of this. You want to know, can I know whether or not I got it right? Well, sure, we know how to differentiate, right? And I could have simplified this. This could have been 2x minus 1 to the 3/2 over 3 plus c. All right, so let's take the derivative. So we bring the 3/2 out front. So that's 3/6 times 2x minus 1 to the 1/2 plus c. And that's going to be multiplied by 2, right? Plus 0, because the derivative of a constant is 0. So 3 over 6, that's 2. The 2's cancel out, and I just have 2x minus 1 to the 1/2, which is the square root of 2x minus 1. That's what I started with, so I know I got it right. Did y'all follow that differentiation? Let's do it again. Let's say this is 1/3 2x minus 1 to the 3/2, right? Bring the 3/2 out front, so we have 3/2 times 1/3. 2x minus 1, decrease that by 1, and then take the derivative of what's inside, which is 2. So the 2 cancels with the 2, the 3 cancels with the 3, and I'm left with the square root of 2x minus 1. So I know I did it right. All right, so if you have any questions about doing a change of variable for indefinite integrals, make sure you shoot me a reminder or ask questions in class.